Okay, I got the question.
So it's loading. I will let you know when we're live, because it's going to be awkward. We will see. Okay, so Daniele tell me that we're visible on YouTube. So this means, I mean, you are. And so if you want, it's 2 p.m. sharp. So I will switch off my microphone and I will start recording the session.
Perfect. So I wait till the moment when I get the message, the yes, yeah, perfect.
Now.
Okay. So I think we can start. So hello, everybody. I am Valentina Franceschi, and I would like to welcome you to our mini symposium, The Mathematics of Vision from Cortical Inspired Modeling to Perception, that I co-organized with Luca Calatroni and Dario Prandi. Today we will have 4 speakers, and I think we are ready to start from the first one, who is Jean Petitot, and he will talk about cortical functional architectures and contact geometry. So the stage is yours.
Thank you. You hear me? It's okay?
Yes, perfect.
Okay. So neurogeometry concerns integrative and functional neuroscience, and it works at the mesoscopic level and does not directly concern the ODEs of neurons or PDEs of neural networks. Its purpose is rather to understand the cortical implementation, the possibility of a cortical implementation of the global geometry of visual percepts as resulting from an integration process of retinal very local differential sense data. And this purpose comes up against a hard problem. The geometry of visual perception involves many differential computations, it's evident. But neurons are essentially point-like processors. They can only code a single numerical value by means of their firing rate. Of course, they are connected and they can transmit their activity along their more or less inhibitory or excitatory connections, but this is radically insufficient to directly implement differential routines. There is therefore a sort of antinomy at the root of a neurally implemented perceptual geometry, how differential routines can be neurally implemented in networks of point-like processors, since derivatives are not point-like entities. Now, it is a key empirical fact that biological evolution has introduced new post-retinal neural modules and neural layers, such as lateral geniculate body, cortical layers, orientation hypercolons, etc., that implement new variables, new post-retinal variables, beyond variables of retinal position. And so we can therefore try to understand how a connectivity, a neural connectivity extended to these new modules and new layers can perform differential computations. Of course, it must certainly have a very, very special functional architecture. But we must also know at the mathematical level under what conditions a point-like functional architecture is able to implement differential calculus. So the hypothesis of neurogeometry is therefore that maybe point-like processors can implement an alternative formulation of differential calculus using what Richard Montgomery called hidden derivatives as new supplementary independent variables, which can be in a second time implemented in point-like processors and interpreted as true derivatives. So these new hidden derivatives must satisfy strong, very strong constraints in order to be interpretable as true derivatives. And for that, the connectivity of the network must be extremely specific. Now, alternative versions of differential calculus do exist in modern differential geometry, since Pfaff, it is a very important and very old tradition, Jacobi, Frobenius, Lie, Darboux, Cartan, Weil, Goursat, etc. And it is these alternative versions of differential calculus which perhaps can solve the hard problem. And to understand why, we have to dive deep into the history of differential geometry. And for some slides, I will speak on the history of differential geometry. The geometrization of the integrability conditions of differential equations have been a revolution very similar to that accomplished by Galois for the resolution of algebraic equations. For a long time, the problem of the integration of differential equations, such as the sum of ai dxy equals 0, was considered as impossible, absurd, meaningless, as it was said at the time, if there was no integrating factor. And Gaspard Monge was one of the first to explain that, he worked in dimension 3, the conditions of integrability means that the solution of omega equals 0 are surfaces in R3, but that when the conditions of integrability are not satisfied, there still exist solutions, but which are one-dimensional skew curves and no longer two-dimensional surfaces. And it was a very a true revolution, this extension of the concept of solution. And from Pfaff to Frobenius, differential geometers had gradually understood the very deep condition of integrability. Omega is a one form, wedge d omega is the differential of omega, equal 0. Monge raised what became 30 years later the Pfaff problem, the well-known Pfaff problem, and he prophesied its importance. Quotation, it was not noticed that this was the beginning of an immense chain to which lay the great difficulties of differential calculus. And from that turning point, from that moment, geometrizing the integrability of differential equations became the problem of analyzing tangent hyperplane fields, kernels of differential one forms, contact forms, etc., etc. And so the basic notion became, at that time, that of a contact element. It was Lie's Flechen element, that is a pair of a point x of a manifold and a hyperplane kx of the tangent plane of M at x. And as you know, Sophie Lie developed it in great detail with a strong sense of the inversion of point of view it brought. And in a beautiful text of 1894, the geometric work of Sophie Lie, Felix Klein emphasized the importance of the change of perspective brought about with this new, clear, and penetrating view, as he said. He explains that Lie introduced new elements of space, much more general than points, and instead of applying the methods of differential analysis to geometry, was interested in the reciprocal and developed the application of geometrical intuition to analysis. And this is the key foundational issue, exactly as in Galois for algebraic equations. The essence of differential calculus shifts from analysis to geometry. And so we can see now why and how point-like processors can be good differential geometers if they are able to detect contact elements. And in the 90s, I developed the following relations between this type of geometry, Pfaffian geometry, and neurophysiology. First, a class of cortical neurons in V1 called simple neurons detect contact elements AP, where A are positions on the retina, and P, a local orientation at A. It was the work of the Nobel Prizes, Hubel and Wiesel. The vibration AP over A, with fibers, the projective line of orientations, is neurophysiologically implemented by retinotopy and orientation hypercolons. Third, the contact structures of the one jets of plane curves is neurophysiologically implemented by horizontal cortical connections. And fourth, the sub-Riemannian geometry of this contact structure is neurophysiologically implemented. In particular, illusory contours can be interpreted as a geodesics. So you see that it is exactly as in general relativity. You need a deeper concept of geometry, Riemannian geometry, to understand how inertial motions of planets can be at the same time very, very complex motions, because the space is curved, is a Riemannian manifold. Here it is exactly the same. You can understand how activated neurons can do differential geometry if they implement contact elements and contact structures of contact elements. But directly, you cannot understand how neurons can integrate partial differential equations and ordinary differential equations. By the way, long-range illusory contours are one of the most striking phenomena of low-level vision. For instance, we can reconstruct the shape, and it is a well-known example of a Dalmatian dog in this very incomplete image. And we will see that they can be interpreted as geodesics of a contact structure for an appropriate metric. And such Brownian models generalize the previous model due to David Mumford and based on the theory of elastica. And they have many applications, in particular for in painting, since to complete a corrupted image, we must construct the illusory level sets that can complete the missing parts. And the following picture shows how a highly corrupted image at the left can be very well restored using sub-Riemannian diffusion. It is Gautier Prandy in painting, and the face of our friend Jean-Paul appears out of the blue. So, simple neurons of V1 are parameterized by triple AP, where A, XY is a position on the retina identified with R2, and P is an orientation modulo pi at A. And so simple cells of V1 constitute a field of orientations, and this field is the basis of the functional architecture of V1. What could be its structure? The first global reconstruction of an orientation field from the sparse local data provided by electrodes, still Hubel and Wiesel works, was inferred abductively in 1979 by Valentino and Carla Breitenberg. And this was long before the introduction of modern in vivo optical imaging techniques. And after Breitenberg, in an astonishing paper of 1987, still before the advent of optical imaging techniques, Nicholas Swindell reconstructed the spatial layout of the orientation map, what are now called pinwheels, and he thus confirmed Breitenberg's abduction. Here you have a reconstructed field of orientation by Swindell, and using a color code for directions, he got an orientation map. I insist and I emphasize the fact that this is a theoretical reconstruction and not at this time an empirical observation. But as you know, Breitenberg's and Swindell's abduction have been strikingly confirmed in the 90s by brain imagery, and you all know orientation maps with pinwheels. Here it is the V1 area of a macaque by Blasdel and Salama. Okay, now geometrically, pinwheels can be interpreted as blowing up of points AI, and the orientation field is the closure of a section of the fiber bundle VG, G for jets, equal R2 cross P1 over R2, defined over the open subsets R2 minus the point AI, the blown up points AI. Over the AI, the closure of the section sigma is the exceptional fiber P1, and these exceptional fibers P1 are contracted and folded onto small neighborhoods of the base points AI to give pinwheels. So there is therefore a 3D to 2D, two-dimensional collapse. An orientation map is in a way a geometric object of intermediate dimension between 2 and 3. And at the limit, when all the points of the base plane R2 are blown up in parallel, we get the fiber bundle VG R2 cross P1 over R2. And so VG can be considered as an idealized continuous model of the concrete neural V1 produced by biological evolution with its spin wheels and orientation fields. But the vibration VG R2 cross P1 over R2 is not sufficient for interpreting P as hidden derivative, in the sense of Richard Montgomery. That is, as a tangent to a curve. For that, P must satisfy the fundamental Pfaff equation, omega equal dy minus P dx equals 0, defining the contact structure of one-jets of plane curves. As you know, a curve, a skew curve in VG is a Legendrian lift of its projection onto the base plane R2, if and only if it is an integral curve of the contact structure. Now, let's remember that the contact structure is left invariant for a group law, making VG isomorphic to the polarized Heisenberg group with its well-known Lie algebra. VG is an nilpotent group of step 2, Carnot group, and you can generalize to the Euclidean group SE2. The contact form of SE2 is cosinus theta dy minus sinus theta sinus theta dx. The contact planes are spanned by the tangent vectors x1 cosinus theta dx sinus theta dy and x2 equal d theta, with Lie bracket sinus theta dx minus cosinus theta dy. It is essentially the red vector. And the xg constitute an Euclidean orthonormal basis, and the distribution C of contact planes is still bracket generating, but SE2 is no longer nilpotent, and the Carnot group VG, the polarized Heisenberg group, is its tangent cone, its nilpotentization. Now, the very key point for the neurophysiological level, which is another striking experimental discovery, is that the contact structure of V is implemented in a specific class of neural connections. Orientation hypercolons correspond to the vertical retinogeniculocortical connectivity, but cortical neurons of V1 are also connected by horizontal cortico-cortical connections inside the cortical layer itself. And such a second system of long-range horizontal cortico-cortical connections is necessary to implement a parallel transport, enabling the visual system to compare two retinotopically neighboring orientations, hypercolons P and PB, over two different base points A and P. Here is a quotation of William Bosking, an eminent specialist of these questions. The system of long-range horizontal connections can be summarized as preferentially linking neurons with co-oriented, coaxially aligned receptive fields. This means that the chain of simple neurons EI, PI is a chain of horizontally connected simple neurons, if and only if it is a discretization of the Legendrian lift of a not too curved base curve interpolating between the AI. And so this means that up to some bound on curvature, the contact structure C is neurally implemented, neurophysiologically implemented in V1. Okay, and now in the last part of my talk, I will come back to curved illusory contours. Variational models have been introduced since the late 70s. They minimize an energy along curves in the base plane, and the best known is the Elastica model proposed in '92 by David Mumford. But for neural models, and not only 2D image processing, it is natural to work in V1 with its contact structure and the Legendrian lifts. And it is here that sub-Riemannian geometry fully comes on stage. The natural idea is to introduce sub-Riemannian metrics on V and look at geodesics models for curve completion and illusory model contour. The sub-Riemannian geometry, as you know, of the Heisenberg group has been explained in the 80s by Richard Beals, Bernard Gaveau, and Peter Kreiner, and it can easily be adapted to the polarized Heisenberg group. And geodesics are projections of the trajectories of a Hamiltonian field of the cotangent space, and using variables associated to the length of the geodesics and the initial conditions, the covector, the initial covector, the sphere centered at the origin and with reduced air, and the wavefront W of H are given by the following equations, where theta is the angle of the tangent. And of course, it is the modulus sine phi over phi, which is very important and explains the strange geometry of the sphere and the wavefront. They are displayed in the following figure, and such a complex behavior is impossible in Riemannian geometry. Here is a sub-Riemannian sphere, and here is a view, an internal view of the wavefront, with the y-axis, which is a degenerate caustic, singularities on the y-axis, and smaller and smaller circles of cusp singularities which converge to zero. And the following figure displays the distribution of the cusps of the wavefront. Okay. And now my last slides are on the geometry of SE2. With Giovanna Sciti and Alessandro Sarti, we studied the passage from the VG bundle with its natural action of the Euclidean group, R2 cross S1, to its associated principal bundle. And we thus go to the model I call the VS equal S2, endowed with its natural contact structure and its associated L-invariant sub-Riemannian metric. And the geometry of the sub-Riemannian spheres and wavefronts is much more complicated, and it was computed essentially by Andrei Agrachev and by his team, Yuri Sashkov, Hugo Boscain, Moïse, Jean-Paul Gaultier, and others. If the lambda I are the components of the covector lambda in the basis omega I dual to the basis xi, the Hamiltonian giving the geodesics is half the sum of the square of lambda 1 and lambda 2. And if H is constant, and if we make the change of variable lambda 1 equals sine of half gamma and lambda 2 minus cosine of half gamma, then gamma satisfies the pendulum equation. And the Hamilton equations are given in function of theta and gamma by the following equations. And so you have a pendulum in the cotangent space which control the behavior of the geodesics. The phase portrait of the pendulum is stratified, and its stratification governs the classification of geodesics. Here is a phase portrait. In magenta, you have the open strata of oscillating motions. In yellow, the rotating motions, and in thick lines, the stratum C3 between the strata C1 and the strata C2, and also point strata, which correspond to the stable and unstable equilibrium. And Sashkov computed all the sub-Riemannian geometry of SE2 using Jacobi coordinates, phi and k, which rectify the dynamics of the pendulum gamma. And in these coordinates, the vertical system in the fibers become trivial because k is constant and phi is linear. And k is the modulus of the elliptic integral associated with the pendulum. It encodes the energy of the pendulum, and phi is the pendular time length. It encodes the length of the geodesics. And for instance, for the C1 stratum, oscillating pendulum, Moïse and Sashkov found the following equation with the Jacobi Sn, Cn, and Dn elliptic function. So we have this formula and explicit formula, and we have similar formulas for the other strata. The sub-Riemannian spheres and wavefronts look a bit like those of the polarized Heisenberg group, but are much more complicated. The fundamental difference is that the y-axis, which was a degenerate caustic in the VG case, splits into 4 branches and an asteroid surface, and the point singularity on it unfolds into small, what I call tetrapaks. We illustrate the case for the radius half pi. The strata Ci are sent by the exponential map into strata WCi, and the following figure displays WC1, the oscillating part of the pendulum, and the C3, WC3, the image by the exponential map of the C3 intermediary strata. So here it is in some sort the half of the sub-Riemannian sphere. But the most complex part of the sub-Riemannian sphere and wavefront is given by the images of the C2 strata with an infinity of singularities accumulating at the origin. So here you have the image of some level lines of WC2 plus for k equal constant, the modulus k equal constant. And so you see these level lines. Here you have another image, more complete image. Now, in the formula for the strata C1 and C2, the Jacobi elliptic function have period. T1 equal 4k of cap k of small k, k is the modulus, and cap k is the complete elliptic integral of the second kind. Yes. And T2, the period for C2 is 4 small k cap k. For C1, you can have a solution of the equation period equal the radius, to take the radius equal to the period, only if t is greater than 2 pi. But for C2, and it is the origin of the complexity, there exists always a solution kr of the equation r equal the period 4k cap k. And for this value, we get exceptional level lines. And for periodicity of the elliptic function Sn and Dn, and the fact that Dn has period 2 cap k, while Sn has only period 4 cap k, the exceptional line LKR is degenerate. I make some pictures. So the value of k for half pi is this value. You have a degenerate level line, but very close to this degenerate level line, you have another degenerate level line. You see the value. For k half pi c, c for critical, you have another degenerate level line. And the surface of the wavefront has an envelope between these two degenerate level lines. And the surface of the wavefront between these two degenerate level lines has a form of a sort of tetrapak, as in the figure. Here you have an image of the surface of the wavefront, where you see in the middle the tetrapak and the rest of the surface at the exterior of the interval corresponding to the tetrapak. And when the radius r varies, the ends of the two degenerate level lines, LKR and LKR critical, run along 4 branches, which splits the degenerate y-axis of the case of the Heisenberg group. And it is my next slide. It displays the sphere and the wavefront of the SE2 Riemannian geometry. So here you see how the C1 strata and the C2 strata are glued together by the intermediary of the C3 strata. And here is another perspective. And by transparencies, you see, as in the Heisenberg group, the circles of cusps converging to the origin. Okay, and so we see that the sub-Riemannian geometry of a Lie group as elementary as SE2 is rather complex. And so my conclusion is that we need this type of geometry, contact geometry, sub-Riemannian metrics of contact structure to understand how the visual system is able to do sophisticated differential geometry with only point-like processors. The philosophical key is that you can implement in point-like processors contact elements and connections between contact elements, even if with neurons you cannot directly solve differential equations. Okay, I hope it was not too long. No, it's okay.
It was a couple of minutes, but thank you very much. It was excellent hearing your talk and all about your view. Maybe one quick question. Does anyone have a quick question?
I have a small question.
Yeah.
Thanks a lot for this enlightening talk. My question is that intuitively I'm always confused when we talk about the need of endowing these point processes, the neural activities being point processes with a certain notion of differentiability. Could we say that the motivation behind this need, this effort, is to try to think neural activity within a context of neural connectivity? And if not, what is the real motivation behind this effort of try to endow the neural activities, I mean, these point processes with a notion of differentiability?
Yeah, how to say? It is exactly as the problem of general relativity. Take classical mechanics. You have empirically complex motions of planets. With Newton, Lagrange, etc., you have fantastic differential equations modeling these very complex motions, okay? Now there is a philosophical problem. Planets cannot compute differential equations. Physically, the only thing that can do planets is to have inertial motions, to be inertial, okay? So you have to understand how inertial motions can be complicated and not only linear motions, as for the Galilean group. And for this, you have to completely change and complexify the geometry. And it was general relativity. In general relativity, the motions are purely inertial. So the planets have nothing to do. The complexity is in the geometry. Okay. For the differential geometry of vision, you have the same thing. This differential geometry must be implemented in neurons. But neurons cannot do differential equations. They cannot compute the only thing they can do is to be activate and propagate activation along connections. This is the equivalent of inertial motions. They do nothing. They are activated by the inputs and propagate. So all the job must be done by the connectivity. So you have to understand how a connectivity of point-like processors, which has only a capacity, the capacity of being activated, can do the job. And for this, you need a geometrization of differential calculus. And the origin of neurogeometry is the discovery that at the retinal level, you have only points. And if you want to compute a tangent of to a curve, you have to do classical differential calculus. But biological evolution invented cortical layers with orientation, with neurons able to detect orientations. And so you can detect with a point-like processor of a higher level produced by evolution, but far beyond retina. It is sophisticated cortical layers which do the job. You can implement hidden derivatives. Okay. And it is because there is this implementation of hidden derivatives that the cortex can do differential geometry. Okay. And so you have to use, in the same sense as Riemannian revolution is absolutely necessary to general relativity, my hypothesis is that contact geometry, invented by Monge, Pfaff, etc., Frobenius, Cartan, Goursat, etc., is necessary to interpret the neural implementation of perceptual differential geometry.
Okay. Okay, thank you. Thank you very much.
So thank you very much for sharing with us your view. I am sure we have a lot of questions more, but maybe it's better if we go to the next speaker, and then maybe we can either contact you by email or discuss after the. Thank you very much. So the next speaker is Noemi Montopio. That now is. She is here, right? Yeah. So I see her. So I guess you would like to share your screen. Mm-hmm. Are you allowed to do it yet? Yeah, perfect.
Yeah, I guess so. Okay. Presentation mode. Okay, can you see it?
Yes, perfect.
Okay.
So yeah, the next speaker is Noemi Montopio, who will talk about from receptive profiles to lateral connections in V1, geometric characterization. So the stage is yours. Thank you.
So hi, everyone. So now I'm currently working as a postdoc at the Neural Computation Lab at the Italian Institute of Technology based in Genoa, but actually the work that I'm going to talk about was developed previously as a part of my PhD thesis that was prepared between the math department in Bologna and the CAMS lab in Paris. And it's roughly contained in these two works. Can you see my mouse? Okay, pointer. Thanks. In these two works published in 2019 and 2020. So we focus on modeling the functional architecture of V1, the primary visual cortex, and the idea was to find an explicit link between the geometry of the feed-forward connections entering V1 and the geometry of the lateral connections happening within this area. So specifically, we characterize the interactions between units in V1 in terms of a distance that is defined on a space of features, and it's induced by the receptive profiles of the cells. So basically, given any family of receptive profiles, we want to develop a method to compute the connectivity pattern associated with them. So I'll start by showing how this distance looks like in the most simplest possible description of receptive profiles, say simple cells in V1, that is a family of Gabor filters with varying positions and orientations. But then our framework also applies to, can be used for modeling the connectivity induced by more realistic representations, including, for instance, orientation maps, or to different types of feature selectivity, and specifically a family of end-stop profiles selected to curvature. And finally, I'll show that we do not need any pre-existing parameterization or ordering on the fiber for our approach to work to compute the connectivity associated to a bank of learned profiles. So first I want to set a few notations. So when I talk about feed-forward connections entering V1, I'm referring to the transformation of a retinal image to the corresponding cortical activation. So an image on the retina is lifted from the original spatial coordinates to a set of cortical coordinates that encode not only position, but possibly other features such as orientation, scale, and so on. So V1 can be modeled as a space of features. Now, on the other hand, lateral connections link units that belong to the same area. So we can think about them as a kernel, a connectivity kernel that expresses the strength of interaction between points of the feature space. So we want to define such a kernel, and we are interested in the emergence of structures, geometric structures that are compatible with the known properties of lateral connectivity. So specifically, we are talking about long-range connectivity that extends beyond the extent of the receptive fields of the neurons, and most importantly, it's orientation specific, as Jean was saying. So it extends along the axis of the preferred orientation of the starting neuron and tends to target cells that are oriented coherently and in line with this axis. So these properties also reflect on the perceptual side through mechanisms that are linked to perceptual integration, so contour integration, that can be summarized by the concept of association fields. So the fact that our perception of an oriented element is amplified by the presence of nearby edge elements that are either collinear or co-circular with it. So feed-forward connections entering V1 can be, let's say, simplified as a linear filtering operation that approximates the response of V1 simple cells to a retinal image. So the input would be a function I defined on the retinal plane, that is our image, and this is filtered by a receptive profile of each neuron. So where the receptive profile is a function describing the impulse response of the neuron, and it's typically defined onto a local domain of the retina that is called the receptive field. So this output H approximates this filtering, the output of this filtering approximates the response of one single cell to the image I. But let's suppose that we have a whole family of receptive profiles. So the simplest possible way in which profiles of simple cells can be modeled is by translations and rotations of one base filter size 0. And so in this case, we would have a family of filters that are indexed by a position xy in R2 and an orientation theta in S1. So the feature space that is associated with this family of filters is R2 times S1 in this case. So the collective response of the family of profiles to the image can now be written as a function on this feature space that associates each point x, y, theta of the space with the response of the corresponding profile to the image I. Now, so as I was saying, we want to starting from any family of filters that represents some set of profiles, of receptive profiles in V1, we want to say something about the lateral connectivity induced by them in terms of a metric on a feature space. Now, in principle, a feature space is any set indexing the family of filters that we are considering. So it can have some pre-existing geometric structures, as is the case for rotations and translations, or also dilations, introducing also scale as another parameter. So in these cases, we have feature spaces that have a product form given by position times some other features. So these other features do not need to be necessarily parameterized with some geometric structure. So for instance, if we suppose that we have a bank of filters that are convolutional filters that are learned from data, in that case, we have the invariance by translations. So we have the first two positional coordinates, but then the third index, sorry, is just an index in this case because the filters are learned. So the features in that case wouldn't be explicitly parameterized. Or even more generally, we can have a bunch of filters with no parameterization of any kind. So I'm talking about a feature space that suggests some sort of geometric structure because I'm about to define one, but in principle for now, I'm calling a feature space just any set that is in a one-to-one correspondence with the set of filters. And in any case, in all these cases, we can still lift an image I to that feature space by means of the filtering operation, so as a function of the feature space. Now, given a set of receptive profiles, the distance that I want to define on the feature space is very simply defined as the restriction of the L2 distance between the filters. So given 2 points P and P0 in the feature space, we are defining the distance between them just as the L2 distance between the two corresponding filters that are psi P and psi P0 indexed by these 2 points in the feature space. So we're defining a metric space. Now in L2, we also have a scalar product, and we use it to define a kernel on the feature space that describes the strength of interaction between two units. Now, if we assume all the filters to be normalized to the same L2 norm, we get that the squared distance is just obtained as a constant minus twice the kernel. So this means that points that are close according to the distance are going to be strongly connected according to the kernel. So now to compute the kernel, what we do is just take the integral of the product between two filters. So basically we are interested in what happens when we superpose the two filters by possibly shifting them. So just to give some intuition, I'm showing here some possible configurations that we can have for Gabor-like oriented filters. So if two filters are oriented the same, but they are just slightly shifted along the the axis of the preferred orientation, what happens is that the product is still positive and the value of their integral, so value of the kernel is still high and close to the maximum. Whereas if the displacement is larger, at some point the filters are not overlapping anymore, and the interaction according to this measure is going to be 0. Or we can have a negative interaction when the displacement happens along the axis that is orthogonal to the preferred orientation, because we have a superposition of lobes with different signs. On the other hand, when the filters are centered at the same point, of course, if their orientation is similar, they're still going to have a strong interaction. Whereas, for example, if they are orthogonal, they don't interact at all. So this was to give some intuition about about why we're defining the kernel this way. Now, as I was saying, as soon as the two filters do not overlap anymore, according to this measure of interaction, we have zero interaction for non-overlapping filters. So, but on the other hand, I was saying that lateral connections in V1 are long-range connections. So to model that, we want to propagate the action of this local kernel by means of an iterative procedure. So this is to obtain a wider kernel that gives a possibly non-zero measure of interaction between two non-overlapping filters. So intuitively, we may think of connecting to these joint filters by taking local steps via a chain of profiles that each connected to the next according to the local connectivity. Or more precisely, what we do is impose a discretized reproducing property for this kernel. So a convenient setting to do this is that of metric measure spaces. So we have defined a metric space, and now we want to define a measure on it. So a possible choice is the spherical house of measure associated with a distance that can always be defined on a metric space. And it's also well behaved with respect to coexisting geometric structure. So for instance, if we have a Riemannian distance and we compute the Hausdorff measure associated with it, we get something that coincides up to a constant with the Riemannian volume form. Or another example is a discrete case that is important for a computational context where the measure just reduces to the counting measure. So now we fix a starting point for our propagation, so a point P0 belonging to the feature space F. And we denote by K1 P0 the local kernel computed around this point. So we fix P0 and we let P vary, the other argument vary. So we also apply the sigmoidal function to the kernel and we normalize it. So this is the generating kernel, let's say, of our propagation. And then we define a sequence of kernels where the kernel of step n is obtained by integrating the kernel of step n minus 1 against the local kernel k1. So this kind of looks like a discretized diffusion on the metric measure space. And also thanks to the relationship between k and the distance d, by applying the sigmoidal function in the generating kernel, we actually obtain an exponentially decaying function of the squared distance that kind of resembles a heat kernel. So as a first example, simple cells in V1, as we know, are often modeled as a bank of Gabor filters obtained by rotations and translations of a filter psi that is given by a complex exponential modulated by a Gaussian envelope. So in this case, the feature space, as I was mentioning before, is the roto translation group, R2 times S1. So this already has a pre-existing geometric structure, a Lie group structure. And this was actually used in previous work by Citti and Sarti to describe the lateral connections of the one in terms of a sub-Riemannian diffusion operator on this space. But in order to define our distance on this feature space, we're not using any of the differential or group structures of the feature space, but just a sort of measure of compatibility between the shapes of the receptive profiles. So the distance in this case can be computed analytically, and it can be shown to be locally equivalent to a Riemannian distance on this space. So we are actually reobtaining a differential structure, and what's more, this Riemannian distance degenerates to the sub-Riemannian structure defined by Citti and Sarti as the scale of the filters goes to 0 and their frequency goes to infinity. So in other terms, when the tuning of the filters to position and orientation becomes infinitely sharp. So here we have two level sets, one level set of the distance induced by the profiles in green, and in red the level set of the distance of the sub-Riemannian distance. So we can see that if we apply our framework to a family of Gabor filters, what we obtain is, as a limit case, an existing differential model of the connectivity of the one. So here's what happens again in the Gabor case when we propagate the kernel. So if we fix a starting point P0, in this case 0 in R2 times S1, we have this on the left, the starting filter, or more precisely its real part. And we can compute the local kernel around this point and propagate it according to the procedure that I was describing before. So the kernel actually around the point is actually a three-dimensional object. So to visualize it, we project it down onto the XY plane by taking the maximum over the orientation theta. And we can also define an association field induced by this connectivity that is composed by the orientation theta that maximizes the kernel value at each XY point. So what we obtain is a connectivity that spreads along the axis of the preferred orientation of the starting cell. And the induced association field also shows patterns of collinearity and co-circularity that are compatible with psychophysical association fields. Now, taking R2 times S1 as a feature space means assuming that over each point XY, we have a whole fiber of orientations, which implements sort of ice cube model of the one. But actually, as also Jean was pointing out before, the distribution of orientation preference over the cortical surface is more of a halfway kind of space. And the hypercolumnar structure is actually collapsed onto a surface forming pinwheel arrangements. So we could, this would mean that for each point XY, we just have one orientation theta at this resolution. And so in other terms, theta can be written as a function of XY. So with this more realistic representation, our feature space becomes bidimensional, and it can be parameterized as a surface contained in R2 times S1. So given by X, Y, and theta of XY, given an orientation map theta. So the distance in this case is computed by only using those filters that lie on the surface, and the kernel, the connectivity kernel, lives on the surface F as well. So the kernel matches the geometry of the orientation map, and we obtain a connectivity that is not only orientation specific, but also patchy with peaks on coherent orientations. So I want to stress that the visualizations here are not projections in this case, because the propagation of the kernel happens within the surface itself, so in this bidimensional feature space. And we're not using the other Gabor filters that live outside the surface. And finally, I want to show two more examples. So first, we computed the connectivity pattern that is induced by a family of end-stopped profiles. So with antagonistic end zones that suppress the response to stimuli that are longer than the central lobe. So this kind of cells have been shown to react to curved stimuli, and previous work has analyzed the relationship between the length of the filter of the profile and the curvature of the stimuli. So we considered different families of end-stopped cells with different length, and we obtained curved association fields with curvature, increasing curvature with decreasing length of the filters, consistently with previous findings. And finally, we computed the connectivity pattern associated with a bank of learned filters. So in particular, we considered a bank of filters learned as a sparse basis for natural images, for the statistics of natural images. And these filters are invariant by translations. So the feature space, as I was mentioning before, is still has a product form where the first two coordinates are x, y coordinates, so spatial coordinates, but the third coordinate is just an index because the filters are learned. So the other features are not explicitly parameterized. And even in this case, what we obtain is a pattern of, in the induced association fields, is a pattern of collinearity and co-circularity, even though the orientation was not explicitly parameterized. So just to sum up, given a set of filters that are modeling some family of receptive profiles in V1, what we propose is an approach to modeling the geometry of the connectivity pattern associated with the set of profiles. And this is built as a sort of measure of compatibility between the receptive profiles, so between the feature selectivity of the two filters. And this gives a local connectivity measure that we propagate to obtain long-range connections. So the framework makes very few assumptions, so it's quite flexible and it can apply to very different banks of filters. So in the Gabor case, we obtained an existing differential model of lateral connectivity as a limit case for our distance. And but then we can also get rid of the ice cube abstraction and model the connectivity associated with a orientation map, or model the connectivity that is induced by profiles sensitive to different features, not only orientation. And finally, as I was saying, we don't necessarily need some ordering on the fiber or parameterization of the features to compute the connectivity pattern associated with a bank of filters. That was all. So thanks a lot for listening and for any questions or comments you may have.
Thank you very much, Noemi, for the beautiful talk. So are there any questions from the others? I have a small one, but...
I have a quick question, if I can.
Yeah, sure.
Yeah, so thanks a lot. It was really clear. It was really, really nice talk. So I wanted to ask you something about this last example you show about these learned filters. So this thing that like you can say something about the connectivity even when you don't have any parametricity is very interesting. I was wondering if you find any sort of analogies in the connectivity for these filters with the connectivity that you find with any family, for instance, of parametrized filters, the one depending on orientation. So like if you can compare really these two connectivities somehow.
Yeah, not in a complete way, but yeah, I had started to do something in that direction. That is specifically trying to see if the modeled connectivity, so obtained from the filter convolution, is kind of similar to to some like differential model of connectivity. For instance, with a like fundamental solution to a Sub-Riemannian Laplacian or something like that. And so, this is not complete, but we were trying to see if there was, in terms of correlation between the two kernels, something, because that means, of course, that means giving a parameterization to those filters. So a way to do that is taking the learned filters and trying to approximate them with Gabor functions. So, and define an ordering on the fiber, and based on that ordering, trying to see if the analytic kernel and the empirical kernel, let's say, are similar. And I don't have any like final results, but it was kind of going in that direction. Yes. Yeah,
it's very interesting, because I think it would be helpful to validate somehow these filters and to see how they perform. That's very interesting. Thanks.
Thank you.
Yeah, let me add that I think that my question was like very related. I wanted to know if you tried, or if you think you expect any like explicit, if you can like extract an explicit relation of a Sub-Riemannian heat kernel, or any like information of this type, like fundamental solution of some Riemannian Laplacians, like in these Kn that you are proposing, but I guess that you kind of answered already. So
I mean, I would have answered the same to this.
Exactly. So you expect it. Okay, so it would be nice to see your future work in this direction then. Thank you very much. Any more questions?
I have a very naive question. I'm a bit not confused, but the learning procedure is based on, when you consider the input images for the learning, for the construction of those learned filters, is there a specific set of input images, or?
In this case, yes. Of course, like in this specific case, this was a dataset of natural images. These are not like, this comes from a work of Olshausen and Field. And so I just used the published algorithm to generate this bank of filters, but it can be done in principle for maybe the first layer of a convolutional network, or any kind of learning procedure from natural images, or even from different sets of images where different feature selectivity may emerge.
Okay, well, I'm asking this question because it would be really interesting to see, for example, if you give a very restricted set, like they do with cats, for example, on the horizontal bars, and then when they observe the cats, they cannot really capture the vertical structures in the nature. And when you do the same with your learning procedure, when probably you would end up with these, let's say, deficient receptive profiles, which could not capture the vertical structures and so on. I mean, this kind of experiments could be validated by your method. It would be really interesting to see this kind of things.
Yeah, I agree with that. I think yes. Since the connectivity that is completely induced by the receptive profiles, I would expect it to be exactly deficient as the filters are. So not able to turn maybe.
Okay, thanks a lot. It's really nice work.
So thank you very much, Noemi. I don't know, maybe it's better if we move to the next speaker. And then again, if we like for more comments on question, we will feel free to contact you by email, or if you agree, Noemi. Okay. Okay.
I need to stop the sharing.
So I can do it for you.
Thank you.
Done. So that Alexei maybe can start his screen sharing. Perfect.
Can you see my screen?
Yeah, we see the small version, and now we see the big one. So perfect. Yeah, very good. So it's my pleasure to have Alexei Mashtakov speaking today about Liouville integrability in a 4-dimensional model of the visual cortex. So please start.
Yeah, thank you very much. First of all, I would like to thank the organizers for the possibility to participate in this very nice mini symposium. I will speak about a 4-dimensional model of the visual cortex, and namely about integrability of the geodesic flow on it. Roughly speaking, this four-dimensional model is an extension of a classical model introduced by Jean Petitot and consequently developed by Giovanna Citti and Alessandra Sarti and many other researchers, which is nowadays is very popular, well-known classical model. But this extension is made by adding...
Alexei, sorry if I stop
Yes.
you, just to be sure. Are you moving the slide or are you
Not
on
yet,
the first?
not yet.
Ah, okay, sorry.
I'm
I
just
thought you
explaining
was
the
sorry.
title.
Okay, that's perfect. Sorry.
So, and this model is an extension which takes into account the curvature of contours. So everybody knows that in the primary visual cortex, there are neurons which can detect the orientation, but also some specialists of vision put forward some experimental data that support that in the primary visual cortex, there also exist the curvature detectors that can detect not only the orientation, but the curvature of contours. And based on this assumption, we consider the four-dimensional model in space of positions, orientation, and curvatures. And there we study the Subramanian problem, which explains the long-range connectivity between the cells in V1. The structure of the talk will be the following. I will start from the classical model and briefly recall you the classical model by Jean Petitot, Giovanna Citti, and Alessandra Sarti, the model, Subramanian model on SE2 group. Then I move to the four-dimensional model. We formulate the optimal control problem that describes the geodesics in this problem, and then we will study this problem of geodesics on this Subramanian manifold. And namely, our topic will be to investigate if the geodesic flow is integrable or not. Namely, can we parameterize the geodesic by some analytic formulas, or it is not possible? And at the end, I will give an answer, but it will be numerical answer. This work is based on joint work with Ivan Galyaev. Okay, let's start. Let me briefly recall how visual information perceived by human brain. The light ray passes through the pupil, goes to the lens, and end up in retina of the eye. Here we have light detectors that collect the information that are activated, and then via the neural path, it sends the information next from retina to LGN cells, where it is kind of smoothened and where some features are already detected. So far, this part, retina and LGN, are well known. I mean, the functional structure of these cells. But then from LGN, the signal passes to visual cortex. And here we have a very complicated structure with many layers, but only first layers have a nice mathematical model of their functions. I mean, the primary visual cortex, V1. If we go further, there are some mathematical models of neural connectivity, but they are quite rough so far. So nobody knows for sure in details how our brain process visual information. But here, now we focus on this area of the visual cortex, the primary visual cortex. There is a well-known mathematical model that describes the neuron cells of visual cortex as a hypercolumns that they can detect the orientations. So hypercolumns consist of the columns which are sensitive to different orientations. They are grouped in hypercolumns that can detect different orientations in the same area of the retina. There are two types of connection. The short range connection, the vertical connection. It means that if one of the cell inside the hypercolumn is activated, their neighbors is activated also with small amplitude. But what is more interesting, there is a long-range connectivity between the hypercolumns in different places of the retina that are far away one from another. But there is a connectivity between the similar orientations. This is called long-range orientations connectivity. And this leads to the Sub-Riemannian model. Namely, it explains this horizontal connectivity is modeled by Sub-Riemannian geodesics, which connect more or less, which connect similar orientations that are located far away from each other. Okay, this classical observation was first done by Hubel and Wiesel in 1959, who discovered the hypercolumnar structure of the visual cortex. And then it was the mathematical model was formulated by Jean Petitot, who initially introduced the Sub-Riemannian structures on the Heisenberg group. And then it was consequently developed by Giovanni Citti and Alessandro Sarti, who proposed to use the group of roto-translations of the plane. Essentially, this model says that the boundary conditions, which is given by point and orientation, is connected by a visual system, by human visual system, via the following variational principle. The recovered arc should have minimal length in the space of position and orientations, and it should satisfy the constraint, so-called the horizontality constraint, that the angle theta is the angle of tangent vector to the curve. This leads us to the classical three-dimensional model of primary visual cortex. Just briefly recall you that the SE2 group can be represented by the following 3x3 matrices, where xy represents the point on the retina, the point on the plane, and theta is the orientation. So that SE2 is a semi-direct problem of R2 and S1. To describe the dynamics of horizontal connectivity, one can introduce the left invariant vector fields, which are obtained by left multiplication of basis left invariant of basis vectors of Lie algebra, which are presented here. In terms of differential operators, these basis left invariant vector fields are written in the following way. So it's the first basis vector field represents the parallel transport in direction theta. It is cosine theta sinus theta. And the second vector field A2 represents the rotation on place. And the third, which will be forbidden vector field, represents the motion in a perpendicular direction to its orientation. Then the Sub-Riemannian problem on SE2 can be written in as the following optimal control problem. Given the dynamics, the control system, gamma dot equals U1 A1 plus U2 A2, where A1 and A2 are given vector fields on SE2, one needs to find a curve that goes from identity of the group and end up to the arbitrary end configuration, so that the corresponding length, Sub-Riemannian length, is minimal. This problem is a well-known Sub-Riemannian problem on SE2. It was studied by Yuri Sachkov and Igor Moiseev, and here the optimal synthesis was obtained in terms of Jacobi elliptic functions. This model has a lot of applications in image processing, in robotics. There are many modifications of the systems. Of this system, for example, we can introduce the curvature of retina and consider the system not in SE2 but in SO3, and it will be the model for contour completion on the retinal sphere, where we take into account the curvature of a retina. Or another modification, we can add the external cost in front of the Subramanian length functional, and then it will be a kind of compromise between observed image and internal geometry of the brain. But here I present one more application where we use the Subramanian geodesics in AC2 for anisotropic, for anthropomorphic image reconstructions. Here we have corrupted image, and at the end we recover the arcs, the missing arcs by Subramanian geodesic in AC2, and we see quite a good result, natural for human eye. And now I move to the topic of the talk, the four-dimensional model of the primary visual cortex. Some specialists of vision, such as Steven Zucker, put forward the experimental data that not only the detectors of orientation are present in the visual cortex, but also detectors of the curvature. And then in the book Neuromathematics of Vision, in the chapter of Jean Petitot, Landmarks of Neurogeometry, there he presents a system that has a which interpretation has an angle type of structure, and where the curvature is taken into account. In this figure, I am trying to explain the the meaning of this model. So now we have in the classical 3D model, we have point and orientation, which is represented by tangent vector here. And we are looking for the curves that connect them, the initial condition and the final condition, and the corresponding curve has a minimum Subramanian length. In four-dimensional model, we add the fourth component, it is which represents the curvature of the contour. And now we want to find the curve that minimizes the energy, that minimizes the Subramanian length, but not in a space AC2, but in a space of positions, orientations, and curvatures. And here it is presented. Okay, let's formulate this problem mathematically. The configuration of neurons now is given by quadruple. It is position, orientation, and curvature. So the configuration space is a direct product of AC2 times R. We introduce a Subramanian structure there. So the distribution is given by a span of vector fields A1 and A2, which is written here. So here the difference with a three-dimensional model is the presence of this additional term k d theta. And we introduce inner product on the distribution delta in a standard way. So omega 1 and omega 2 are dual basis form, which is dual to vector fields A1 and A2. Delta eta zeta is a Kronecker symbol. The curve gamma from 0 to t to m is called horizontal if its tangent vector belongs to the distribution delta for almost every t. Then Subramanian minimizers are horizontal curves that have minimal length. The length here is defined in standard way. It is integral of norm of velocity vector. And Subramanian geodesics are curves whose sufficiently short arcs are Subramanian minimizers. Next, we will study problem of Subramanian geodesics. They are found by application of Pontryagin maximum principle to the system. But first, let's formulate it as an optimal control problem. Okay, we have a dynamics, gamma dot equals u1 a1 plus u2 a2. It is linear on controls. A1 and A2 are given vector fields. One needs to find the trajectory, Lipschitz curve, that transfers the system from given initial configuration Q0 to given final configuration Q1, so that the length, Subramanian length of the curve, is minimal. Let's make a few remarks. First, due to invariance under parallel translations in rotation in the plane XY, without loss of generality, we can reduce the problem from arbitrary Q0 to the following. So we can put the initial condition in the origin of XY plane and set theta 0 equals 0, but K still has to be done. I mean, has to be fixed. It is some constant, which is not necessarily 0. We can't restrict it to 0. And the second remark, there is a square root under this integral, which is not, which can be simplified actually by virtue of Cauchy-Schwarz inequality. We can remove the square root and study the problem of minimizing the action. But now, if here the final time was free, now we fix the final time. But this problem is easier because there is no square root and it is smooth function, smooth quadratic function. It will be easy then to apply Pontryagin maximum principle in this formulation. But before application, the Pontryagin maximum principle, one can ask if solution exists. Namely, do we have the horizontal curves that connect any two given boundary conditions? The answer is yes. It is guaranteed by Shou-Rashevsky theorem. If we compute the commutators and then put them into determinant, compute the determinant, they are linearly independent in every point. So system is symmetric by controls, and then we have complete controllability. Existence of optimal controls followed by Filippov's theorem. Then we obtain the following result. For any given initial and end conditions, there exists an optimal trajectory connecting Q0 to Q1. Let's apply the necessary optimality condition, Pontryagin maximum principle. We write a Pontryagin function, which has the following form. Here we have nu equals -1 for normal case of PMP and nu equals 0 for abnormal case of PMP. The PMP says that if U and Q are optimal control and optimal trajectory correspondingly, then the following condition holds. First, it is a Hamiltonian system, which is in classical Darboux coordinates is written in the following way. Then the maximum condition, the Pontryagin function attains maximum on extremal controls. And the non-triviality condition, the initial covector shouldn't be 0. Let's go to abnormal case where nu equals 0. We introduce the following coordinates, hi, which are written here. The Pontryagin function is linear on u1 and u2, and then it is unbounded if h1 square plus h2 square are unequal 0. It means that they both should be equal 0. And then we write the Hamiltonian system, which has the following form. Here, A, B, C, D are components of the initial covector in Darboux coordinates. Then the maximum connection, the maximum condition of the Hamiltonian system implies that U1 should be that U1, the first control, equals 0. And then we come to the following theorem. Abnormal external trajectories have the following form. So x and y and theta are constant, they are 0, but we have a change of curvature which can be done in different directions. I mean, increasing or decreasing. And here for extremal trajectories, U2 can switch from +1 to -1 as many times, infinitely many times. There is no restriction. But of course, from it is easy to see that optimal trajectories among them will be only those who has either +1 or -1. So where U2 is fixed, because it is not optimal to go in opposite direction if you already went in one direction. Okay, then let's go to the normal case. Here we also introduce the same coordinates hi. Then the Pontryagin function has the following form. The maximum condition implies that U1 and U2 are equals H1 and H2. So this is expression of extremal controls. Then the vertical part of the Hamiltonian system for a joint covector is written here. So why I used here this canonical Darboux coordinates, because it immediately gives us two first integrals, A and B. So this will be important next. But in this coordinates, the system is not very beautiful. But if we use HI coordinates, so it has already observable form. It is more elegant. So this is the Hamiltonian system for normal geodesics. Okay, then we a few more simplifications. Let's use the natural parameterization. I mean, we can parameterize the geodesics by arc length parameterizations, where sum of squares of U1 and U2 equals 1. Then the Hamiltonian is half, and then we can introduce the polar angle alpha, and we end up with the following theorem that naturally parameterized normal extremal trajectories are solution to the following Hamiltonian system. The question arises, can we solve this system? Can we find a solution in some analytical form? And this is exactly the question of integrability of the Hamiltonian system. So the system, the Hamiltonian system is called Liouville integrable if it has, so if its dimension is 2D and it has D functionally independent first integrals in involution, then the system is called the Liouville integrable. And this is enough to guarantee that such a parameterization of solution exists. I must say that it is not a common case that sub-Riemannian structure is integrable. There are several examples. First was in 1997 by Montgomery and co-authors, who showed six-dimensional Carnot group which has a non-integrable geodesic flow. Also, there are some numerical experiments of Carnot groups with Grove vector 2, 3, 14 and 2, 3, 14 and 2, 3, 8, 2, 3, 5, 8. Sorry, and also they showed that their non-integrability is present. But in this work of Lev Lukotseyevsky and Yuri Sachkov, they showed that all the Carnot groups of step 4 and higher already are not Liouville integrable, so there is a chaotic behavior. So let's take a look on our system. We have this system, and we need to find four functionally independent first integrals in involution. We have the Hamiltonian, and we have also these two integrals A and B that I showed in the beginning, and they are indeed functionally independent in involution. But we don't have one more first integral, so we needed to show Liouville integrability. So far, this is an open question. If I mean analytic form of this fourth integral, but numerical simulations show us that it exists. Namely, we use the Poincaré map for analysis of integrability. The Poincaré map consists in following. We need to find the periodic trajectory, and then to find a transversal submanifold to this periodic trajectory, and shift a little bit and choose the initial condition in a neighborhood of periodic trajectory, and then to compute the trajectory of the Hamiltonian system till the moment it crosses the transversal manifold again, and then the second iteration, and so on. And we have the images of Poincaré maps here. If they are aligned in some good continuous curve, then it shows that there is integrability, and it shows the presence of one more first integral. And if they are located somehow in a chaotic way in this plane, then it shows a chaotic behavior. Okay, here we find we can take independent system of four equations from the Hamiltonian systems, and then we find a periodic trajectory, which is written here. The period equals, it is written here, and the transversal manifold here is kappa equals 0. Then we propose the following experiment. In the next figure, we show 4 random initial values from a small neighborhood of the initial value that corresponds to a periodic trajectory, and then compute the Poincare map for 1000 iterations. And we obtain these nice smooth curves. So, and it is clearly shows that this system is Liouville integrable. But the question is to find this remaining first integral and then to find the exact parameterization of the geodesics. Okay. Summing up, we considered the 4-dimensional Subramanian model of the primary visual cortex. We proved the controllability of the Hamiltonian of the control system and the existence of optimal controls. We applied the Pontryagin maximum principle, necessary optimality condition, find the explicit parameterization of abnormal geodesics, derive the Hamiltonian system for normal geodesics, and numerically investigated Liouville integrability of normal geodesic flow. So the next step is, which is quite challenging, to find this remaining first integral and after to find the exact parameterization of the normal geodesics. Thank you for your attention.
Thank you very much, Alexei, for your talk. Are there any questions in the audience? Maybe I can start with a small one. Sorry, Emre, do you want to?
No, go ahead after you.
Okay. So, yeah, I was wondering, do you expect that, like, a couple of things. First, do you expect that this, like, synthesis of geodesics, say, this geodesic can be used to reconstruct any better the, like, I don't know, illusory contours or anything from the, say, more imaging point of view, or not? And related to this, do you expect that there's any particular role played by the abnormals in this game from, say, the modeling perspective, or not?
Mm-hmm. No, I think the abnormal is more like a mathematical subject. So I think they do not play essential role in cortical connectivity. But normal geodesics, I mean, of course, it has to be checked, the difference, for instance, in image and painting and image reconstruction problems, also in the modeling of illusions, optical illusions, everything has to be checked. It is hard to say now, because I didn't do these experiments. To perform them, we need this the form of geodesics. I mean, so far it is hard to say. Will it model better? Will it work better for some image processing applications or not? So it's hard to say so far.
Yeah, thank you. We will, again, also in your case, we will wait for the next results to know. Yeah, thank you very much. Are there any more questions?
I have a question. Alexei, you mentioned that due to Chaussy-Reshevsky theorem bracket generating condition, the existence is always there for the solutions of the optimal control problem defined in this 4-dimensional geometry, if I understood right. Could you say, what could you say about the uniqueness? Because, I mean, okay, existence is over there, but could you guarantee uniqueness as well for any?
No, of course not. I mean, I'm quite sure that there are Maxwell points where distinct
on the cusp points
geodesics matter with the same length. I mean, it already happens already in the EC2 and in the Heisenberg group. So Jean Petitot in his talk showed this wonderful pictures of wavefronts where and the cut locus where different geodesics meet with the same time. And of course, there is no uniqueness. And I expect from this system even more complicated behavior because it has higher dimensions.
Yeah. Okay, thanks.
I just wanted to ask a quick question, because in the case of
when you look at the system with only the orientation there, you have your cost that is essentially minimizing the curvature, right? More or less. So here you're adding the curvature, and what are you, did you study what are you minimizing with your cost from the point of view of, from the perspective of curves in the plane?
So it can be actually better understood in let me find the slide. Yeah, so in classical SE2 model, I mean, let's for a while forget about T-parameterization and let's stick to arcs of the geodesics, which are projected to the plane that have no cusps. Yes, that can be parameterized by arc length on a plane. I mean, of course, even in SE2 case, there is almost all geodesics. There is a point where this parameterization
they go down.
But if we consider these arcs, and when we do this in SE2, then our control actually we control by theta dot. So we have x dot equals cosinus theta, y dot equals sinus theta, and theta dot is our control. So we control by curvature. But when we consider four-dimensional system, we let theta dot equals k, but we control now by k, by theta double dot. So we control by derivative of curvature. So it's kind of how to say, higher order. Maybe.
Yeah, so you're controlling this. The derivative. Your cost is something like the derivative of your curvature.
Yes, yes.
How quickly the curvature changes. Okay.
And then the meaning of this functional is the length already in space of these positions and and curvatures, not of orientation, but positions and curvatures. But the orientation is obtained from curvature, so it's not already independent. It is. It is obtained from curvature. So if we have curvature, and then we can compute the tangent vector, and then we can compute all the trajectory.
So yeah, sorry to stop you, to interrupt you, but I realized that we need to pass to the next speaker now, because at 4 we have the micro talks. Sorry. So yeah.
Thank you very
so
much.
We have. I'm sorry, Alexei. Thank you very much. And again, we will contact you by email or anything more. Yeah, to have. Okay, so I'll stop his presentation, and we have our last speaker, who is Emre Baspinar, and he's starting his screen sharing now. Okay, very good. Let me apologize with Gregory. Okay, sorry. The reminded me that we are a bit late. So we are happy to have our last speaker today, who is Emre Baspinar, and he will talk about a biologically inspired model for Poggendorf type illusions. It's your turn. Thank you.
Thanks a lot for the introduction. As Valentina said, I will talk about a biologically inspired model which we use in order to generate Poggendorf type illusions, and it's a joint work with Luca, Valentina, and Dario. Before I start, I would like to give a brief outline of the whole talk. First, I will provide some general information about cortical modeling and about the notion of subramanian geometry, which actually have been explained in quite some detail by previous speakers. And in the second part, I will present a cortically inspired model for Poggendorf type illusions. And finally, I will quickly wrap up by mentioning our future plans and in which ways we are in terms of research regarding this work, regarding the continuation of this work, which we will see. Okay. Primary visual cortex is the main part of the brain which is responsible for the first step processing of visual input which we collect from nature in order that we perform proper visual perception. And this part of the brain contains a specific family of neurons which we call simple cells. The particularity of simple cells is that those cells are sensitive to, they can extract the information related to several visual features such as orientation, frequency, phase, color, and so on. And in fact, right now, thanks to their orientation selectivity, sensitivity, we're able to distinguish between the different angles of the rotating bar on the screen. So how do those cells achieve extracting the information related to those visual features? Well, by using their so-called receptive profiles. So what's a receptive profile? It's basically the impulse response function of a simple cell. So once we're exposed to some visual input, the neurons on the retinal line produce some spikes which are transmitted through specific pathways to the primary visual cortex, to the simple cells in the primary visual cortex. And each simple cell gives a response to those spikes. And these are what we call receptive profiles, the impulse response functions of these simple cells. And mathematically, we can model the receptive profiles by using Gabor functions. One of the key features of Gabor functions, and which is particularly important for us, is that any Gabor function, say a generic Gabor function, psi, which is sensitive to the visual stimulus located at the point with the compounds x and y on the two-dimensional image plane, and which is sensitive to the objects, to the stimulus, which is in alignment with the direction corresponding to the orientation angle theta, can be obtained from a reference function psi 0, which we call Gabor mother function, and which can be expressed, as Noemi showed more explicitly, in terms of a localizing Gaussian window and the wave content. And the relation between these generic expression of a Gabor function and the Gabor mother function is found through the following coordinate transform, which is represented by capital A, and which basically says that, well, take your Gabor mother function psi 0, which is presumably located at the origin of the two-dimensional image plane, M, which is two-dimensional Euclidean plane, and translate it to the point with the compounds x and y, and rotate at that point your translated Gabor mother function by the orientation angle theta. And there you will find your Gabor function, your receptive profile, corresponding to the simple cell, which is sensitive to the stimulus located at the point with the compounds x and y, and which is sensitive to the stimulus which is in alignment with the direction corresponding to the orientation angle theta. Well, at every point on the two-dimensional plane, two-dimensional image plane. Well, by the way, I mean we assume that image plane and retinal plane and cortical layer they're identical, so we ignore those retinocortical mappings. So at each point on image plane, we find those column-like structures which we call orientation fibers. And orientation fiber contains the Gabor functions or the receptive profiles, which are rotated by all possible orientation angles. And the collection of all these orientation fibers comprises up to what we call the set of receptive profiles. In short, the set of receptive profiles is the set of receptive profiles shortly contains the receptive profiles, Gabor functions, corresponding to all possible combinations of translations and rotations. And this set of receptive profiles is associated with the well-known hypercolumnar architecture of the primary visual cortex, the architecture which was discovered and reported by Hubel and Wiesel in their Nobel Prize work. And this hypercolumnar architecture was proposed to be modeled by Hoffman in terms of a contact bundle structure. Later on, by Jean Petitto and Yannick Tondu, this idea was improved further. And in this contact bundle structure, they provided a boundary completion approach. Moreover, they provided a geometric interpretation of the association fields, which were reported by Field, Hess and Hayes as the psychophysical representations of the neural connections which are biologically implemented in the primary visual cortex. And this construction, this framework, which was provided by Petit and Tondu, was developed further later on by Chit and Sarti, where they introduced a group-based approach, and where they proposed to model this hypercolumnar architecture and the functional connectivity within by using the sub-Riemannian geometry of the group of rotations and translations, or shortly SE2. And we use the geometric framework which was provided in this last work, rather, as the geometric setting in which we propose our algorithms generating Pogoń type illusions. So let me say a few more words about this geometrical setting and its relation to relation to receptive profiles. So to each one of those receptive profiles in the set of receptive profiles, we can assign the following one form, which is represented by lambda, and which depends on the orientation angle parameter theta. This form is particularly important because it's the main mathematical instrument which models the orientation selectivity of the simple cells. Since it gives its maximum response, which is the unit response, once its orientation angle parameter theta coincides with the direction of the vector field x3. So what's the particularity of this vector field x3? Well, it's the vector field which is in the direction of the maximum gradient direction of the receptive profiles of the Gabor functions. In other words, Gabor functions, just like the one form lambda, give their maximum responses once their maximum gradient direction coincides with the actual gradient direction of the two-dimensional image, of the objects in the two-dimensional image, just like in this example, just like in the case of this example, disk image. And in this way, Gabor functions can extract the boundaries of the objects found in the given two-dimensional image. Okay, and this one form relates the receptive profiles to the subroomanian geometry of SE2 because it naturally directly induces the horizontal tangent space corresponding to the subroomanian geometry of SE2. Since by definition horizontal tangent space is the kernel of the one form lambda, in other words, it's the span of two horizontal vector fields, x1, as we saw previously in talks of previous speakers, the vector field in the tangent direction to the objects in the given two-dimensional image, and x2 is the vector field in the direction of in the orientation dimension in the three-dimensional geometry. And horizontal tangent space can be thought of as the analogy of the Euclidean tangent space. In other words, in this particular geometry, we define any differential operator, say subroomanian Laplacian, subroomanian gradient, subroomanian curvature, and so on, by using only these two horizontal vector fields. And it allows, I mean, the geometry itself is three-dimensional, but we define all differential operators in terms of those two horizontal vector fields. And this allows us to take advantage of the high anisotropicity of the geometry, where we find a good representation of the extracted visual information, which in this case is the orientation information corresponding to the given two-dimensional image. And why do we consider this geometry as a good model of the hypercolumnar architecture and the functional connectivity within, related to the primary visual cortex? Because it provides a good model of the neural connectivity in the sense that the projection of the horizontal integral curves, those are the integral curves along the horizontal vector fields x1 and x2, and the projection of those integral curves, those horizontal integral curves onto the two-dimensional image plane, as we see on the right-hand side, coincide closely. They are good approximations of the actual association curves, as I mentioned a couple of slides ago, which were reported by fields S and highest, and which we can consider as the psychophysical representations of the actual neural connections within the primary visual cortex. Okay, so having in hand this geometric setting, now we would like to provide an evolution procedure. An evolution procedure for the evolving neural activity in order to generate Poggendorff type illusions. So first, let me say briefly what we mean when we say Poggendorff illusions. When we say Poggendorff illusions, we refer to the misperception of two parallel transversal oblique which are interrupted by a blocking bar. And an example of such illusions can be seen in this illustration here. For example, here we see the black and blue lines as if they were continuations of each other. However, the real case is actually not. I mean, actually, the red and black curves, black lines are the continuations of each other, not the blue and black ones. And this misalignment in our perception, visual perception, is what we call Poggendorf illusions. And these kind of illusions can be induced by test images such as the gradient, the sinusoidal gratings, which are interrupted again by a blocking bar in the middle region, and where the Poggendorf illusions are induced. I mean, in the middle region. And our aim is to reproduce those Poggendorf illusions by using such test images. Well, this problem was studied by Hoffman, Smith, and later on by Ahmed Wackerman from different points of views, and more recently, and more important to our case, by Franceschello, Mastakovcic, and Sarti. Those illusory patterns were proposed to be modeled as the geodesics in the Subramanian geometry of SE2. And later on, by Bertagno, Calatrone, Francesca Lamprandi, two algorithms, which they named as three-dimensional Wilson-Cowan and three-dimensional local isochromatic equalization algorithms in the Subramanian geometry of SE2, again, the same Subramanian geometry, were proposed in order to generate those Poggendorf illusions. And for us, these two algorithmic procedures provide the departure point of our study. So I will try to explain those two algorithms, and then I will show in which way we contribute and provide our novel algorithms, starting from those two. So both of those algorithms are based on 3 steps, where the first step is what we call the lifting. And the lifting procedure provides the output responses of the simple cell receptive profiles to a given image, which is represented by capital I, which can be thought of as this two-dimensional image with circles with different radii. And it's obtained via the convolution of the given two-dimensional image I with the rotating filter banks of the receptive profiles. At the end, we end up with the lifted version of the two-dimensional image, which provides a good representation of the orientation information within the two-dimensional image, but now represented in the three-dimensional Subramanian geometry of SE2. Once we obtain those output responses of the simple cells via lifting, the idea, which was proposed in Bertagno et al., was to model the neural activity evolution starting from those output responses by using a Wilson-Cowan type equation system, where the lowercase a represents the evolving neural activity corresponding to the neuron located at the point psi in the Subramanian geometry SE2. Here, psi is just a shorthand notation of x, y, and theta. And where lambda is a parameter, is a constant, and where calligraphic I and calligraphic U represent the neural interaction term and the external stimulus. Here we see that the external stimulus consists of 2 parts, where the first part is a weighted version of the initial output responses, the result of the lifting, and the second part, tilde O, is the lifting of a blurred version, a smoothed version of the input image. And the reason for that this second part was included was the will to take into account the contrast effects of the pixels surrounding the region which we focus on when we look at a two-dimensional image. I mean, when we focus on a region which is surrounded by rather bright pixels, we perceive the region which we focus on as brighter than actually it is. And if the pixels surrounding this region are darker, then we perceive as darker than actually it is. And this effect, this contrast effect of the surrounding pixels, were taken into account via this second term, tilde O. And the neural interactions were modeled as the convolution, three-dimensional convolution of the firing activity function sigma, which is a piecewise linear function, and which takes as input the relative neural activity with respect to the average gray value. With a neural interactivity term. where the neural interactivity kernel, W. And one thing which is important to be mentioned is that in this setting of Bertalmi et al., this kernel was chosen to be a three-dimensional Gaussian. However, three-dimensional Gaussian cannot capture the anisotropic structure of the Subramanian geometry. In other words, it's not really compatible. It's not a compatible operator with the Subramanian geometry of SE2. And this is actually the point where we contribute. We will see that we replace this neural interaction term, this convolution, with a more compatible numerical procedure, but more compatible with the Subramanian geometry of SE2. Okay, at the end of the evolution, the third step is back projection. So it's basically at the end of the evolution of neural activity, projecting back the image by integrating over the orientation fibers the evolved neural activities, and to come back to the two-dimensional image plane, where the goal is to see well-produced Poggendorf illusions, Poggendorf type illusions. This algorithm was named as three-dimensional Wilson-Cowan, and the second algorithm, three-dimensional local histogram equalization, was following quite a similar approach. However, the only difference is that now the input of the firing activity is not any longer the relative activity and relative neural activity with respect to the average gray, but it's rather the differences, localized differences of the neural activities, evolving neural activities. This small change had important consequences, as Bertalmi, Caseyes, Poroins, and Ricci showed in 2007. They showed that once this change is done in the formulation of this system, this system could be written as an energy minimization problem, where these solutions, minimizing energy, the solutions minimizing the energy, were providing the patterns along which the neural activity propagation was taking place. And this was in coherence with the efficient representation principle, which basically says that, okay, neural responses are self-adaptive in such a way that they minimizes the redundant statistical information extracted from a two-dimensional image. In other words, they provide the most efficient representation of the visual information extracted from the image by spending the less amount of sources. And back projection, again, is exactly the same as before. And this algorithm was called three-dimensional local histogram equalization. So what we propose is, well, the first step...
Sorry, let me stop you. Just to say that we have 4 more minutes, just so that you can organize your...
Okay, no problem, thanks. Okay, and what we propose is that the lifting is exactly the same, but the second step, in the second step, we replaced the neural interaction term, calligraphic I, which was modeled as the convolution in the previous setting of Bertalmi et al., with a Subramanian heat diffusion iterative procedure, where L is the Subramanian heat diffusion operator, which is expressed in terms of the horizontal vector fields x1 and x2, and a coefficient beta, which guarantees the unit coherency. And thanks to this operator, we are able to restrict the diffusion to be along the horizontal integral curves, which are the models in the models of the neural connections within the Subramanian geometry. What we do is at the end of each step of the Wilson-Cowan type neural activity evolution equations, we perform another iterative procedure, the Subramanian heat diffusion equation, and feed the result of this procedure into the Wilson-Cowan type equations as the neural interaction term. And we repeat this procedure at each step of Wilson-Cowan type equations. And we call, well, at the end, back projection is again the same. We call this system the Subramanian Wilson-Cowan, Subramanian because now this second procedure is more compatible with the Subramanian geometry. And in a similar way, we apply this same idea to the second algorithm, which was proposed in the previous setting of Bertalmi et al. And we end up with a Subramanian local histogram equalization algorithm. Okay, very quickly, I will show some results and then finish the talk. On the left column, we see the results of the previous setting of Bertalmi et al. both Wilson-Cohen and local histogram acquisition. On the right column, our setting, and we see that in the Wilson-Cohen case, our algorithm can produce the illusions, albeit they're low quality. However, in the previous setting, they cannot be produced at all. In the local histogram acquisition, both settings can produce the illusions, but our framework can preserve, in addition to producing the illusions, it can preserve the rest of the image. Okay, that's open access work recently published. So if you want, if you're interested in, you can go to the website of Journal of Imaging and have a look. So let me finish the talk by mentioning the future work. Okay, we would like to study also other illusions, in particular tilt illusions. We would like to also study the spatial frequency effects on these Poggendorf type and also on tilt illusions. And we are actually in the phase of studying bifurcation analysis on these algorithms in order to see that which parameter region produces illusory patterns and which parameter regions not. Okay, I think that's all from my side. Thank you. I hope I'm in time.
Yeah, so thank you very much, Emre, for the very nice talk and also for running fast at the end. Do we have any very quick question? We have 1 minute according to the schedule. So yeah, it's strange if I ask any questions because I'm a co-author of the work. So, well, if there are no more questions, we will just thank the speakers, all the speakers of the session. And so it was great having you all and sharing your ideas with us. And as always, I hope that there will be the possibility to meet in person and discuss without this Zoom thing. And so see you the next time, and thanks a lot again. And yeah, thanks to everyone. Thanks, Gregory. We are okay now.
Yeah, no worries.
Sorry, I was worried at the end because actually I understood that we were very late. But
no, that's fine.
Okay.
We're all at the same page because we're running 3 mini symposia in parallel, and so we're synchronizing now.
Yeah,
so
exactly.
What I will be doing is that I will be stopping the recordings and stopping the broadcasting on YouTube. So I'm doing right.